Welcome. This is a San Francisco Bay Area ACM talk. Tonight's talk is Deep Networks, our Kernel Machines. The presenter is Pedro Domingos. He's a professor of computer science at University of Washington. So just for a little background about San Francisco Bay Area ACM. So we were founded in 1957. Our objective is promote knowledge of modern computing. We're focused on creating community, support networking and hiring. We only have $20 for an annual membership fee. You can see about 140 of our past talks on our YouTube channel. We have 2 monthly meetings like this, general computing one, which is typically the 3rd Wednesday of the month, and a data science SIG, typically the 4th Monday of the month. We work with other societies such as IEEE and Valley ML AI. So some upcoming webinars. On Wednesday, March 17th, we have AI Trust, adversarial attacks on AI ML models, and defenses against attacks. And then Monday, March 22nd, we have a deep dive into AI and deep learning infrastructure with Lambda Labs. Wednesday, on April 21st, we have lessons and opportunities in large-scale networks with smart help applications. If you'd like to ask any questions, you can go into the Q&A on Zoom for requests. Please keep your questions to a moderate length. Please speak closely to your PC. Or actually, we're just handling the Q&A on text. And I'll read the questions to the speaker and he can answer. I'd like to introduce tonight's topic. So deep learning successes are often attributed to auto-discovery of new representation of the data, rather than relying on handcrafted features like other methods. We'll show that deep nets learned by standard gradient descent are equivalent to kernel machines, a learning method that simply memorizes the data and uses it directly for prediction versus a similarity function, which is the kernel. This enhances interpretability of the deep network weights. The network architecture incorporates knowledge of the target function into the kernel. And there's also a paper that this is based on. A little background of our professor, our speaker. He's a professor of computer science at University of Washington. He's also the author of The Master Algorithm, a worldwide bestseller, introducing machine learning to a broad audience, winner of SIG-KDD Innovation Award, winner of IJCAI John McCarthy Award. Please help me welcome Pedro Domingos. Thank you very much.
Hi, everyone, and thanks for attending this talk, and thanks to SF Bay ACM for inviting me. This is going to be a fairly short talk based on a paper with exactly 1 theorem. So there should be plenty of time at the end for questions and discussion. It's just 1 theorem, but it has a lot of interesting implications, as you'll see. And the main idea of the talk is summarized in the title: Deep Networks are Kernel Machines, which at first may seem very surprising, but hopefully by the end of the talk, this will make a lot of sense to you. So the biggest selling point of deep networks has always been that they they can discover new representations of data instead of having to rely on predefined features. And I and others have always found this very attractive, but at the same time a little unsatisfying, because there's this intuition that they learn representations and there's some vague arguments, but nothing very concrete. So part of the goal here was to try to understand what is really going on when deep networks supposedly discover new representations. And in fact, what I have found is that in reality, all that's going on is that there's a kernel. The kernel is learned, but then all that the deep network, regardless of architecture, is doing is comparing, the test example with the memorized training examples using that kernel, and then outputting the class with the highest, value of the discriminant function, and so on. And this, by the way, is not just true of deep networks. It's actually true of any model learned by gradient descent, which is actually a very large chunk of machine learning. So this result, I think, actually has a lot of generality and goes some way towards the whole research agenda that outlined the master algorithm of unifying the different machine learning paradigms. So in particular, this shows that deep networks are subsumed by kernel machines, as are a number of other things. Now, one of the really nice things about this is that it really improves the interpretability of deep networks. In the same way that representation learning has always been the biggest selling point, the biggest Achilles heel has been that the network weights are very opaque. It's a big mess. Nobody really knows what's going on there. And thanks to this result, actually, we now have a much better understanding of what is going on there, and it's not that mysterious at the end of the day. The weights of a deep network are really just a superposition of the training examples in the kernel space, in the feature space of the kernel. And so we can actually look at what is going on in a lot of learned deep networks just by looking in terms of this kernel that I will describe. Another very important point is that the role of the architecture of the network in this view is to incorporate knowledge into the kernel. And again, I think this is a very interesting point because a lot of how people often describe deep networks is that they're very empirical, there's no knowledge involved, unlike other methods. And naturally, as it turns out, there is a lot of knowledge involved in deep networks. That knowledge is encoded in the architecture, and people have spent a lot of effort encoding knowledge into the architecture. We didn't used to be able to do that with kernel machines, and in fact, that was a disadvantage of kernel machines. We just had these generic similarity functions. And now, thanks to this result, we actually know how to incorporate the same knowledge that we incorporated in the deep architectures into kernel machines. And as I said, there's a whole bunch of implications that I will touch on. What I'm going to do is first give the basic background that we need to understand this theorem, which is actually not that much, and then present the theorem and the proof, which is actually simple enough to fit into a few PowerPoint slides, and then discuss some of the implications and some of the future research directions that might follow from here. So, kernel machines. What is a kernel machine? Most of you probably know this, but just to go through the basics, a kernel machine is a model of this form that you see on the slide. The prediction is just a sum over all the training examples of the kernel between that example and between that example and the test example. And you can think of the kernel as a similarity function, so it's higher if the examples are closer together in some space, the kernel space to be more precise. So these kernels are weighted. We add a constant, and then we may pass through a nonlinearity. For example, in classification, it might just be a threshold, and that's our output. And as you can see, there's a number of important things in here. One of them is the kernel. Maybe the most important one is the kernel. The kernel may be predefined, and most of the time it is predefined. It's something like a Gaussian kernel, or a polynomial kernel, or even just a linear kernel, which is just a dot product. But the kernel can also be learned. And in fact, there's a whole subfield of kernel machines or support vector machines that are also known, concerned with learning kernels. And in fact, as we'll see, that's precisely what deep networks are kernel machines with a type of learned kernel. And we're going to see exactly what that kernel is and how it's learned. The way I've expressed kernel machines here is slightly unusual in that I just have those parameters AI there. Often you will see this as AI times YI, where YI is the class of the example. The reason I'm using this form, so you can just replace the AI by AI prime YI star, where YI star is the true class of the example. The reason I'm using this form is that A, it simplifies the notation, but also more importantly, B, that in this way it applies not just to supervised learning where there is a YI star, but to forms of unsupervised learning like kernel PCA and density estimation, kernel density estimation, and so on. So bear that detail in mind as we go through this. Now, it's very well known that you can look at kernel machines as a special kind of a neural network, right? You can just think of the kernel as one layer, and then the combination of the kernels as the output layer. So we've known that for a long time. Now, in the other direction, however, it would seem that deep networks are not reducible to kernel machines for the simple reason that there are various proofs that there are many functions that can be expressed exponentially more compactly with the deep network than with a network with only one hidden layer. And in a kernel machine, there is only one hidden layer, which is precisely the kernel comparisons. However, there's a very important subtlety here, which is just because a network with many layers can in principle represent an arbitrary function, doesn't mean that function will actually be learned in practice from a given data set using gradient descent. And as it turns out, gradient descent is a sufficiently strong restriction that it implies that the models learned by that simple method actually have a specific form, namely the specific form of a kernel machine. And perhaps that is not so surprising if you think about how simple and myopic gradient descent is, right? It's just a local learning procedure. So, you know, in some ways we've been giving it more credit than it really deserves. I mean, the simplicity is good, but also comes with some limitations. So here's a brief reminder of how gradient descent works, again, just to get the notation and basic concepts down. So we start, so we have a predefined architecture. We start with an initial weight vector, typically random. And then the gradient descent just goes through a series of steps, where in each step S, as you see here, what you do is you subtract from the current weight vector the gradient of the loss function with respect to the weights times the learning rate epsilon, which is typically a small quantity that ensures that this all converges. And the loss function is typically just a sum over all the training examples of some measure of how much the true class of the example, which we know because it's in the training set, differs from the predicted one. So this is how gradient descent works. And really all that I'm going to show here is that this and this are equivalent, in the sense that if you learn a model, any model, by this algorithm, then what you get is necessarily of this form, which again might seem surprising, but after you see the proof, you'll probably think, actually, I don't know why people didn't think of this before. So how does this happen? Well, in particular, deep networks and other models learned by gradient descent are kernel machines with a specific type of kernel, which I call a path kernel. And really, the path kernel is the essence of this whole talk and of this whole line of reasoning. So let's see and try to understand what it is and why it's interesting. So the path kernel between two examples, two data points, x and x prime, is really just the integral. Let me first give the definition and then the intuition, and then get a little bit more formal. It's the integral over the path traced by the weights during gradient descent of the dot product of the gradient of the function of the model at one example and the gradient of the function at the other example. So you take the gradient at x, you take the gradient at x prime, you do the dot product, and then as the weights evolve, the weights change, therefore the function and its gradient change, and so this dot product changes. The integral, or if you will, the average of that over the entire training path is what the path kernel is. So I'm expressing it as an integral because, as is usually done in analysis, I'm taking the continuous limit and imagining, infinitely small steps, so that gradient descent, instead of being a discrete series of steps, is just following a continuous curve. And of course, the reason to do that is the usual one, is that it really simplifies the analysis and kind of lets us see things a little bit more clearly. So what is the path kernel measuring, right? What is the idea behind this? The path kernel really is just measuring how similar is the variation in the model at the two data points as the model evolves during training. So here's a graphical illustration of that. Let's suppose we have a very simple case where there's just two weights, so the weight space is just the plane. And now we have a starting point, which is W0 here on the lower left corner. And then this curve that you see is the path followed by the weights during training, and it ends at W final, where gradient descent has converged. And you see a number of intermediate points here, W1, W2, W3, and so on. And at each of these points in weight space, you can compute the gradient of the function, the gradient of the model of y at any training point. In particular, you can compute it at the test data point that you're trying to classify or do a regression for, as you see here in black. So the arrows in black are the gradient of the function y at x with the weights of w1 and then w2 and so on. You can also do that for each of the training examples. So for example, here's the series of gradients for the example x1 is in red, and the series of gradients for example x2 is in blue. Okay, and now of course you can do the dot product between the black vector and the red vector, right? And there's the dot product of the gradient at x and the gradient at x1, and you could do this at every point along the path, right? And now notice that the dot product, at least in this example, the dot product between the gradient at x and the dot product and the gradient at x1 is on average higher than the dot product between the gradient at x and the gradient at x2, because the black vector lines up more with the red vector than with the blue one. So if you average this over the entire path, what you get is, on average, how similar the gradient for x is to the gradient for x1, and how similar it is to the gradient for x2. And the result of this is that if, on average, the gradient for x is more similar to the gradient for x1 than to the gradient for x2, then that example is going to have a higher weight in predicting the class of x. So the y1 will have a higher weight in predicting x than y2 will have, other things being equal. And this is really, in essence, all that's going on. Now, if you follow the machine learning theory literature, you're probably familiar with this concept of the neural tangent kernel that has emerged in the last few years. The main paper was published in 2018 and has become popular for doing things like analyzing the convergence properties of gradient descent and what happens, or gradient descent in deep learning, and also what happens in the limit of an infinite number of weights. And you probably recognize the neural tangent kernel as the integrand of this kernel that I have here, right? So the dot product, the neural tangent kernel is really just the dot product between the gradient of the neural network at two data points. What I'm going to do with it here, however, is very different from what's been done before. There's no, this is for finite, normal networks, if you will. It's not the infinite weight limit. I'm also not going to be looking at convergence properties or such things. I'm really going to be looking at properties of the representation. So here's a definition of a neural tangent kernel. And in fact, I'm going to drop the neural from that name because it really isn't neural. It's well defined for anything that is continuous and differentiable, and that we can apply gradients to. So I'm just going to call it the tangent kernel. So the tangent kernel associated with the function f sub w of x and the parameter vector v is just the dot product of the gradient of the function with respect to the weights so the kernel between 2 points x and x prime is a dot product of these of this gradient at those 2 points taken at the parameter vector v. So it's a function fw of x and the parameter vector, and it takes the gradients at that point v, and the dot product of the two gradients at x and x prime is the kernel between x and x prime. And now the path kernel associated with the same function and with some curve c of t in parameter space, where t is what the curve is parameterized by, is just the integral of the tangent kernel over that curve. Okay, so if you understand the tangent kernel, in a way, the path kernel is a very natural construct. Is just the integral of the tangent kernel along the path that the weights follow during training, right? The tangent kernel is a notion that applies to a static network. Typically, people focus very much on the initial network, but you can just, compute it at every point during learning, including the final one, and then the integral of that, or the sum, if you take finite steps, is the path kernel. And with these two definitions, we're actually ready to state the theorem. It's a bit of a mouthful, but we'll just go through it. And again, the basic idea is very simple. It's really the title of the talk. So suppose that you have a model. Y is f sub w of x. F, of course, has to be a differentiable function of w, of the weights. It actually doesn't have to be a differentiable function of x. X can be anything. It could be a discrete structure, which is nice. because it makes this very general. And y is going to be learned, as usual, from a training set of pairs xi, where, as I said, xi can be any structure, and yi star, where yi star is the true prediction for xi. We have m of these examples. And we're going to learn the model by gradient descent with a loss function that, of course, has to be differentiable and also is additive, as almost all loss functions used in practice are. This just means that it's a sum over the examples of a loss for each example, and the loss for one example, as usual, is just a function of the difference between, or a function of, the true class of the example, or the true output, could be continuous, could be a probability, etc., of the true value, the true output value, and the predicted output value. And the learning and the gradient descent, as we saw before, is done with the learning rate of epsilon. So what the theorem says is that under these conditions, the limit when the learning rate tends to 0 of y, of the function, of the learned function, the model, is just a standard form kernel machine. Sum over the examples, I of the example weight AI times the kernel between the test example x and the corresponding train example xi plus a constant b. Okay, and of course the theorem doesn't just say this; it actually says specifically what the AI, b, and k are, and that's actually that's half of what's interesting about this. It's not just the general statement. So in particular, AI, as we'll see in more detail a little bit later, is the average derivative of the loss function, for the ith example along the path weighted by the corresponding tangent kernel, with a negative sign because we're doing gradient descent. If it was ascent, it would be positive. That negative sign is going to be there, but we're not going to worry much about it. B is just the initial model. It's the initial random network that doesn't depend on the training examples. And of course, the kernel is the path kernel that we've just been talking about. So that's the theorem. And you're probably wondering, why would this be the case, right? Where could this possibly come from? Well, actually, the proof, as I alluded to earlier, is actually quite simple. Simple enough that, you wonder why people didn't think of this before. As far as I know, they didn't. And it's simple enough that we can actually go through it in just a couple of slides. So here it is. It's like 7 steps, 6 or 7 steps, depending on how you count. So we start with just gradient descent, and in particular, with the continuous version of gradient descent, which is called a gradient flow. And this is just a differential equation for how the weights evolve over time. And the equation is that the derivative of the weights over time, remember that weight W in this equation here is a vector of weights, is just minus the gradient of the loss function with respect to the weights. Where does this come from? Actually, it's very simple. If you look at the gradient descent equation, subtract WS from both sides and divide both sides by epsilon, then what's left on the right-hand side is just minus the gradient of the loss. On the right side is just minus the gradient of the loss. On the left side, what you get is the change in weights with epsilon divided by epsilon. And if you let epsilon goes to 0, of course, that just becomes the derivative of the weights, with epsilon. So here's the gradient flow. And now the next step is to just draw on the chain rule, which is, after all, what backprop is based on. Not much more than that if you think about it. And the chain rule just says that dy dt, i.e. the change in the output of the model with time, is just the sum over the weights of the partial derivative of y with respect to the weight and the partial derivative of the weight with respect to time, right? This is really just the chain rule, nothing else. Notice that, and conveniently for us, you can also express this as the dot product of 2 vectors. The first vector is, of course, just the gradient of y with respect to the weights. And the second vector is just the derivative of the weight vector with respect to time, right? So this is just another way of writing the same equation. And now if you look at these 2 equations that we have here, the gradient flow equation and the chain rule, you see that we can replace dw dt in the chain rule by its expression given by gradient flow. And what you get is here at the bottom. It says that the derivative of y with respect to t is just the dot product of the gradient of y with the gradient of the loss function. And remember, all these gradients are always taken with respect to the weights, right? And this is a very simple equation, but it's actually a very interesting one, right? We already see here, you're probably already kind of guessing where the main result is going to come from. And in fact, it's, all that it took was this, small substitution to kind of see what's happening here, right? What I'm saying is that the change in y when I do a step of gradient descent is in essence just a dot product of the gradient of y and the gradient of the loss, right? So it's a dot product of two gradients. Now, the next step, as some of you have probably already guessed, is to take advantage of the additivity of the loss, right? The gradient of the loss is a sum of gradients of the loss for each of the examples. So we can replace it by that. And then, of course, we can push the sum of the examples outside of the dot product. And now what we get is this, right? The derivative of y with respect to time is just the sum over the examples of the gradient of y and the gradient of the loss for that example, okay? And now, remember, the loss, right, of an example with respect to the weights is really a composition of two things, right? Because like the loss is a function of yi, and then yi is a function of the weights. So we can again apply the chain rule and say that the derivative of the loss with respect to the weights is its derivative with respect to y, with respect to yi, which I'm gonna call L prime I, and the gradient of yi with respect to the weights, okay? And if I replace, the gradient of Li by the product of using the chain rule of Li prime and the gradient of yi, and then again push the Li prime outside the dot product, I get this expression. The derivative of y with respect to time is just the sum over all the examples of the corresponding loss derivative times the dot product of the gradient of y, of the gradient of y, the test data point, and the gradient of yi, the example that I'm summing over. Okay. And notice that at this point, this is starting to look like what we know, right? In particular, the tangent gradient, the tangent kernel has just appeared here, right? I actually now have here the gradient of y dot product the gradient of yi, which is the tangent kernel. Okay.
We have a couple of questions, if I could.
Sure, go ahead.
So one is asking, could you please go over what the black vector represents once again?
The black vector in the diagram?
Yeah, here.
Yeah, so the black vector is the gradient of the model for a test example x, okay? So x1 and x2 are training examples, okay? But x is the example that I'm trying to classify. You can think of what I'm doing here is I'm taking my test example x and I'm running it through the same process that I ran the training examples to, except that, of course, it's not allowed to influence the change because it was not available at training time, right?
So x1 and x2 are training data, and x is the scoring or the inference data.
Exactly. X is the example that I'm trying to classify. I'm looking at a new picture and I'm asking, is this picture a cat, right? And remember, when I trained the network, I have the sequence of networks that I trained all the way, with all the parameters. I have the initial network with initial weights, and then the next one, and then the next one. I could actually apply each of those networks to my test example, right? And I can compute the gradient of that function at my test example. And this is exactly what I'm doing here, okay?
Okay. Another question, this is from Pradeep. I worked on deep networks directly, but I've not worked on kernel machines. What is meant by a kernel machine? Is there a good resource to read on about kernel machines?
Yeah, certainly. There's books, there's textbooks that have been written just about kernel machines. There's a number of tutorials. I mean, again, prior to deep networks, kernel machines were the most widely, researched and perhaps applied machine learning method. However, all you need to, I mean, again, there's infinite variations of kernel machines, but the basics of a kernel machine are really in just this one slide. I just store all my training examples. And then what I do to classify a new training example is I compare the new example of each of those using the kernel. And, for example, it could be just the dot product, or it could be some Gaussian function, something that is a function that is higher when the examples are more similar. And then I weigh my predictions by that kernel and by this coefficient AI, right? So it's a weighted, so my prediction for a test example is just a weighted average of the classes of the training examples. So if my test example is similar, for example, in terms of the pixels or in terms of the features that I computed from the pixels, like SIFT features, for example, as people used to do. If my test example is more similar to the examples of cats than it is to the examples of dogs that I have in my training database, then cat wins, and I predict that this is a cat. Okay.
I believe earlier you said that support vector machines were like one common type of kernel machine.
Yes, in fact, the two names are almost interchangeable. You could have a support vector machine with just a dot product kernel, which is what people started doing back in the 1960s when it was just a theory. You could have kernel machines that are not support vector machines, but in practice, the two are the same thing, right? Every support vector machine has a kernel, and you can, you can look at any kernel machine as a type of support vector machine. Support vector machines are called support vectors because usually when you learn the weights, hopefully most of the training examples wind up with the weight of 0. And the ones that remain are what are called the support vectors, because they're the vectors, examples are vectors that support the boundary that is being defined. If you change one of the support vectors, you change the boundary between the classes. If you change one of the non-support vectors, then nothing happens.
Okay. Another quick question. This is a mechanic one I'll answer. Is this being recorded? Will we get a link later? The answer for that is just check the SFBay ACM on YouTube, and we have a YouTube channel, so things will be posted there. So you can just look at that for the link. Monica asks, can there be too many competing path kernels? How do we determine the appropriate number?
No, so there is only one path kernel, right? So I think I understand the question.
So that's just like the forward propagation is the path.
Yeah, so a path kernel is a kernel, right? And the kernel is just a function of two examples and some parameters possibly, but I give you two examples and I get back a real number that tells me how similar they are, okay? So if you give me two examples, two data points, whatever they might be, you get a path kernel, right? And of course, you could define different path kernels, and in fact, every neural network, every model with every weight vector defines a different path kernel. So yes, there are as many path kernels as there are differentiable functions. Okay. Now, what happens when you're actually learning a deep model or applying it, right? Is that again, as in any kernel machine, you are computing the kernel of your test example with each training example. Okay. So if I have 1,000 training examples, I actually have 1,000 kernels being computed. And then the predictions of each of those examples are going to be weighted by the corresponding kernels. So if I have an example that is very similar to my test example according to the kernel, then that example is going to have a high weight in classifying the example. And what I said is just true of all kernel machines. In particular here, we're looking at path kernels because as it happens, deep networks are path kernels. But the idea of how you apply a kernel and you compute it for each example, and then you do the average is the same for all kernel machines.
A last question, Lecha, can you continue on with your presentation? Pradeep is asking, can we apply the same regularization or dropout techniques to kernel machines as well?
We can apply, so let me answer that question the following way. Around your basic gradient descent learning algorithm, there's all of these things that you can do, right? Meta learning, AutoML, even simple things like picking parameters by cross-validation, et cetera, et cetera. All of those things can be done and they don't change the basic result. Because what's happening inside them, if it's still gradient descent, the equivalence to kernel machines via path kernels still applies.
Okay, thank you.
All right, so yeah, please let me know if you have any other questions. So continuing from here, so here's where we were, right? What we have found is that the derivative of y with respect to time is just the sum over the examples of the tangent kernel for the test example and the training examples weighted by the corresponding loss derivatives. Okay, so we have an expression for dy dt. So now, of course, this is just basic calculus. If I want to know the final y is just the initial one plus the integral of dy dt over the path taken by the weights, right? Now, what is the initial y0? Well, obviously, that's the initial model, typically the deep network initialized with random weights. And now I have the integral over the path c of t of the expression that I have above. Okay, so this is just integrating the dy dt that we had to give us y. And if you look at this expression at this point, we're almost there, right? This is already starting to look a lot like a kernel machine and like the path kernel, right? The main thing that you have to do here is switch the order of the integral and the sum over the examples, which of course you can do because an integral is just an infinite sum, right? And then again, you also want to, to get the path kernel, finally the last thing that you need to do is push the li prime outside the integral. And the way we're going to do that is just by replacing li prime by its weighted average, weighted by the corresponding tangent kernel. And then what we get is this. Okay, so here's the expression that we get. Y is yi0 minus the sum over the examples of the path kernels weighted by the average loss derivatives. And if you compare this with the expression that we saw before for a kernel machine, we're done, right? B is y0, right? So that B coefficient is just the initial model. The AIs, right, are just minus the average loss derivatives, and the kernel is just the path kernel. And with these coefficients and the path kernel, the deep network or the model that you just done by gradient descent is in fact a kernel machine. Okay. So at this point, you've seen the theorem and you've seen in a simplified form why it's true. Now, before looking at what are some of the interesting implications of this, there's I think a number of important remarks to make. Some of them are caveats, some of them are extensions, others are related things. One important caveat is that if you look at this expression, it's not quite the same as a typical kernel machine. And the reason it's not is that in a typical kernel machine, the coefficients do not depend on x. They only depend on the training examples xi. And here they depend on x. Okay? So AI in particular is a function of x via the loss function and its derivative. And b, is the function of x because the initial random function is a function of x. But there's a couple of important things to realize, one of which is the AIs actually still play the same role here that they play in a support vector machine or even in a perceptron, which is that the examples that the loss is more sensitive to during learning have a higher weight. Okay? And the other important thing to realize is that they may be functions of x, but the AIs only depend on x and xi via the kernels. Okay? So the key defining characteristic of a kernel machine is that the examples enter the model only through the kernels, and that's exactly what is happening here, right? And whether those examples enter the form in exactly the traditional kernel machine or various variations or this one is less important than the fact that they only enter the model through the kernels. Okay, so the final model is really the sum of two things: the initial random model, which actually doesn't even depend on the training data, and the model and the learned model, in which the examples enter only through the kernels. Also, you can, if you don't like this idea of the kernel of the coefficients depending on the test example, you can actually use an alternate formulation here. Some of this is more a matter of taste and aesthetics. which is you can actually let the loss derivatives be part of the kernel. Okay, there's nothing preventing you from doing that. In which case, the coefficients the AIs just become they're all -1. Okay. Now, of course, what happens here that's like not entirely elegant is that you need to define the loss function for your test example, and you don't know what the true class for the test example, otherwise you wouldn't be classifying. But if you define it as being a constant for all the test examples, then you just get a kernel. Or you could have a kernel that doesn't include that, but is not asymmetric, but is not symmetric, which kernels are supposed to be. So it's your choice which of these formulations you like most. There's actually a third one that we will touch on later, which in some ways maybe in the long run is even the most interesting, which is that you can actually just look at this as a form of boosting. But let's hold that thought for the moment. Go ahead.
A quick question from Bill. He said, I'm puzzled. The definitions, proof, and operations seem to be commutative, yet the structure of the weights in a neural net are different depending on the order the samples are added in. What am I confusing here?
First of all, remember, I'm actually going to touch on that in just a second. What I'm doing here, so what I have done here so far is for batch gradient descent. Right? This is gradient descent where all the examples are used at each step, which is actually the gradient descent. This is actually the correct gradient descent, if you will, for which we have convergence guarantees and whatnot. And in batch gradient descent, the result is independent of the order of the examples, right? Because remember, the result of batch gradient descent only depends on the examples via the loss, and the loss is just a commutative sum over the examples, okay? Now, as it happens, this also applies to stochastic gradient, which is, of course, what people use in practice, and I will get to that in just a second. Does this answer the question?
I would believe so, yes.
If not, you can ask, a follow-up question.
Sure.
So another interesting remark to make is that this result is nice because it's very general. In particular, it's independent of the loss function, but it actually, becomes in some ways more intelligible if you look at it for specific loss functions. So for example, if you're just doing least squares regression, which is maybe the most widely used of all these things, then what the AI is just the loss derivative is just the difference between the true class and the predicted one. And I think that actually gives you a lot of intuition as to what's happening, right? When you're learning, with the path kernel, because then what happens is if you're, the more off your prediction is from the true value of a training example, the more influence that example is going to have on the result, because it's going to have at that step, right? And then you sum this over all the steps, but that will be remembered by the path kernel. So examples that at some point have a lot of error have a lot of weight that comes from having a lot of error, and because there's a lot of change to be made in order to get that example right, and that propagates through to the test example. Of course, the other important example is cross entropy, which we typically use for classification, at least in deep networks. And there, the loss derivative, the AI, is just 1 over pi, where pi is the probability of the true class for the ith example. And then the same idea, you can apply to the likelihood if you're just learning, if you're doing probability density estimation and so on. So here's another question that may have occurred to some of you. The treatment that I've done here is just for a plain vanilla loss function, but often people use a regularized loss, where to the loss you add a regularizer. And the question, of course, is, does this still apply there? And it's not hard to see that, yes, it still applies there. The only thing that adding a regularizer to the loss function does is that it adds a term to B, right? And the term that it adds to B, not surprisingly, is actually the dot product, again, of two gradients. This time, instead of being the gradient of the function and the gradient of the loss, it's the gradient of the function and the gradient of the regularizer, right? So no big surprise there. Another important extension, which I just alluded to, is that this also applies to stochastic gradient, which is, I think, important from a practical point of view. And of course, the difference between stochastic gradient and batch gradient is that in stochastic gradient, you do not use all the examples at each step. You only use typically a random subset, which could be smaller or larger, could be as small as 1 or in the limit as large as the whole training set. And you compute the gradient for those examples, and then you take the gradient descent step. And extending this results this theorem to stochastic gradient, all it requires is to multiply each example at each step by an indicator function that is 1 if the example is included in the batch at that step and 0 otherwise. And then what this means is that the integral that you get at the end of the day is a stochastic integral, but again, the demonstration is more complicated, but we understand stochastic integrals pretty well, and this is a pretty well behaved one. So again, the result is essentially unchanged. Here's another very I think worthwhile remark to make. You can look at this result as being the generalization to multi-layer perceptrons of a classic result for single-layer perceptrons. In fact, in the paper that originally introduced kernel machines under the name of the potential function method back in 1968, I think, by this classic paper by Aserman, Braverman, and Rosenau, which is really the ancestor of the entire area of kernel machines and other things as well. One of the things that they did in that paper was to show that the simple one-layer perceptron, which of course already existed at that time, was a special case of a kernel machine with the kernel being the dot product, which I always thought was a fascinating result, because you look at kernel machines or nearest neighbor on the one hand and the simple one-layer perceptron on the other, and they seem to be completely different. And yet one is a simple case of the other with a particular choice of similarity function, namely the dot product. And what happens with the more general result that I have here is that if the model that I'm learning is linear, it's easy to see that then the gradient is just the input vector, as a result of which the path kernel just becomes the dot product of the two examples. Okay? And then this, of course, retrieves the special case of the perceptron. It also retrieves the special case of linear regression, right? So linear regression is just a kernel machine where the kernel is the dot product. But of course, the intriguing here is that result extensible to multi-layer networks and more complicated nonlinear models? And prior to this paper, the answer would have been no. And precisely the novelty here, if you will, is that actually yes, that same result remarkably extends to arbitrary nonlinear models and in particular to multi-layer neural networks. This is also related to a result that is perhaps less well known, but that I also find quite remarkable, which is that if you know the history of deep learning, right, there was this wave in the 50s and 60s, and then things died out for the next 15 years after the Perceptrons book by Minsky and Papert. But then there was this thing that brought them back in the 80s, which was Hopfield networks. So John Hopfield proposed this new type of network called a physicist at Caltech proposed this thing called the Hopfield network, and there was an enormous amount of excitement about this, and and that was the second wave of neural networks, in which backprop was born, and Boltzmann machines, and a whole bunch of things that we use today. And then Richard Lippmann and a couple of co-authors actually proved that a Hopfield network is actually just nearest neighbor with a particular distance measure, and the distance measure is just Hamming distance. So Hopfield network was for binary outputs, and turns out that the class predictions made by the Hopfield network, after all its fancy, nonlinear, attractor dynamics and all this physics motivation, is just nearest neighbor with Hamming distance. And I've always been kind of intrigued by that, and and there's actually a few other results like this that always raise this question of like, well, at the end of the day, maybe neural networks are not as different from these similarity instance-based kernel-based type of methods, and a lot of my motivation for doing this work was to try to suss out exactly what that relationship is, and the fact that maybe they're more similar than they seem to be at first sight, and that does indeed seem to be the case. So one final and important remark here, which is the following. What I've done here, right, if you look back at the theorem, is the limit when epsilon tends to 0, right? So I am assuming that the learning rate is sufficiently small that I can approximate the path taken by the weights during gradient descent by a smooth curve, okay? And this, of course, is the standard assumption in the theory of these things. In fact, you can't even guarantee that gradient descent converges if the epsilon is not infinitesimal. So theoretically, this is a very reasonable assumption. Also, in practice, it's probably a good assumption, because you have to make the epsilon very small in order to avoid divergence. Values of 10 to the minus 3, 10 to the minus 4, minus 5 are commonly used. Having said all that, it's still an open question whether this result still applies in the finite step regime. So there is that important caveat to what I'm doing here. Okay, so as I said, this theorem is very simple.
A couple of questions, if that would be all right.
Sure, go ahead.
So one from Yang. It looks like L prime bar is doing the heavy lifting, which depends on the kernel itself. In general, are the A sub i's expected to be kernel dependent?
I wouldn't say that the Li bar is doing the heavy lifting. The heavy lifting is being done by the path kernel, right? If you took out the Li bars and left the path kernels, you'll still get something meaningful. If you took out the path kernels, you wouldn't get anything useful. Now, what is Li bar, right? Li bar is the average loss, right? So it's an average loss, right? Now, and again, the intuition for that is what I explained before, is that examples that have higher loss during training, right, influence the learning more. And they're also the examples that in some sense are hard to classify, again, as in support vector machines and in perceptrons, and therefore they're the ones that should have a higher weight. So this is what that loss is doing, right? Now, there's an important point here, which this is a loss weighted by the tangent kernel, okay? And this is why the Li primes depend on the examples that the tangent kernel is in there, right? But the tangent kernel is in there just to average the loss, right? And as I said, if you don't like that formulation, you can use the formulation where that term is absorbed into the path kernel. You can think of like there's unweighted path kernel and there's weighted path kernel, right? And with the unweighted path kernel, then the AI primes just become 1 or minus 1. So it's kind of a matter of taste.
And then another from Govind, are kernel machines more expressive than neural networks?
Well, they are not. So good question, right? But the answer, as I said in the beginning, is they are not, because I can take any kernel machine and kind of like just by inspection say this is a deep network, right? Where the hidden layer is just a computation of all the kernels, right? If in a basic, in fact, there's a well-known type of neural network. I mean, maybe not so well-known these days, but back in the 80s and 90s, it was one of the most widely used because it was successful in practice, called a radial basis function network. A radial basis function network is just a one hidden layer neural network where the nonlinearities are Gaussians. And each Gaussian is the Gaussian, over the difference between the input example and one training example, okay? And if I change the kernel to a different kernel, then what I get is the different nonlinearity in the hidden layer. But at the end of the day, right, if you look at if you squint at the form of a kernel machine, right, you can say like, oh, this is a neural network with 2 layers, right? This G is the output layer, and the K's are the hidden units, okay? Yeah. So the fact that kernel networks are deep networks, we've known that all along, right? What is more remarkable is that the equivalence also holds at least approximately in the other direction. So really, you could sum up all that we know as, essentially kernel machines and deep networks are equivalent. Right? You can look at any model, in one class and see it as the other.
Yeah, I mean, I remember using RBFs, and we would initialize the basis functions with like a k-means, or just to do clustering, 1 cluster per RBF.
Yeah, exactly. And people,
which is a data example, basically.
Yeah, there were various ways of trying to select the initial, those centers, and doing k-means was a natural one. People sometimes did things like EM, and and so on. And then and then probably what you did was you learned the final layer just by linear regression. Yeah, so there's various ways to do this. Yeah.
Okay. A question from Bill: does a kernel machine recursively capture the quote layers in a neural network?
Well, if you think about it, right, what is happening here is that I guess another way to ask that question is, where are the hidden layers in this kernel machine now, right? Because it's a kernel machine with a path kernel, right? And if you look at it at this level, it seems shallow, right? Well, of course, the answer is that the depth is inside the kernel, right? What's happening here is that the kernel that we're using is actually a much richer thing than we had back when we were just using Gaussian kernels or polynomial kernels or things like that.
I mean, isn't the path kernel is what's capturing the multiple layers?
Exactly. So again, if you look at what the path kernel is doing step by step, right, at each step, it's actually computing the full network at that step, right? But there's an important twist here, which is, unlike in a deep network where the only thing that you see at the output is the output weights, right? Here, right, I actually have a gradient vector. I'm doing a dot product between gradient vectors, each of which includes the weights at all the layers. Okay, so in the path kernel, the weight, no matter how deep inside the network it is actually expressed in the dot product at the output, right? Which suddenly now makes the whole network, even though the depth is there, right? Like what is going on now is actually much more transparent than what was going on before.
Okay, thank you. That's caught up on the questions for now.
Mm-hmm. So let's look at some of the interesting implications of this theorem. And first, let's look at the implications for deep learning, and then at the implications for kernel machines, and then finally at the implications for other models, because after all, this is about anything learned by gradient descent, not just deep networks. And perhaps the first important, I think, implication of this for deep learning, as I alluded to earlier, is for interpretability. Right? The big disadvantage of deep learning is that it's so opaque, right? And you don't understand what's going on, which makes things hard both for transparency and to explain decisions and to improve the models. And now you actually know what's going on there, right? Is that those weights look opaque, but they're just a superposition. They're just a sum of the training examples in a particular feature space, namely the feature space of the path kernel, right? Quick parenthesis, in kernel machines, one of the founding results of kernel machines is that the kernel machine is always equivalent, or the kernel, right, is always equivalent to a dot product in some feature space, right? And even it could be infinite in the case of a Gaussian, but it's always a dot product in a feature space. And that's very nice for the purposes of analysis, because now everything that we know about linear math still applies. And you can, any algorithm that just depends on dot products, like PCA, for example, can be extended to the nonlinear case just by using what is called the kernel trick, right? And now that same kernel trick actually helps us understand what is going on in a deep network. In particular, right? Think about it this way, right? Here's a diagram of what is going on here. I can look at the model here as a not a black box but a blue box, right? It's just, well, in goes my query example and out comes the answer, and I really don't know what went on there. Just some very big computation. But another way to look at it is that no, actually what that model is doing implicitly is that it has stored all the examples from 1 to m, and then what happens is that I take the query, I compute its kernel with each of the examples, I multiply by the corresponding weight, and then I just superimpose all of them. I add them up, right? And that's what my answer is, okay? So now I can understand deep networks, no matter how complicated, as just being superpositions of the training examples, right? And I can try to understand what's going on by looking at what each example is doing in turn and just adding them all up, right? And one of the main advantages of that for interpretability is that one of the most popular methods, maybe the most popular method to interpret neural networks or deep networks, is to try to look at the distance between the training examples and the test example in some space, like Euclidean space. Oh, like this, I'm classifying this as a cat because the nearest examples in Euclidean space or some other simple space obtained by PCA or something like that, the nearest examples are cats. But these methods don't work that well at the end of the day. And now we understand why. The idea is actually a good one, but they're doing it in the wrong space, right? What matters is not whether the two examples are close in Euclidean space. What matters is whether they're close in gradient space, which is where the path kernel is being computed. So now what I actually want to do, if you want to interpret the output of a neural network, is you project the examples onto gradient space, and then in that space, you look at what the closest examples are. And I haven't done that experiment, but it's, I think, an interesting one to do, is to see how much the closest examples in gradient space predict the class, the actual class of the whole network. If they predict it well, in some ways, most of what the network is doing is quite redundant, right? It's just, the other examples are just kind of like acting as noise. And maybe this actually also gives you a way to simplify the network. But either way, I think it's actually a big improvement in terms of our ability to understand what a deep network is doing. Another interesting implication of this is for understanding the empirical behavior of deep networks. One of the things that's puzzling.
Some questions on interpretability. So one person, Eric, was saying, when I look at the graphic, it reminds me of attention in neural networks. Are they in any way related?
I'm not sure what similarity between this and attention you have in mind. I guess maybe what you're thinking of is that in attention, what I do is give more weight to some features than others in a example-dependent way, right? You could look at what the path kernel is doing in similar terms for some classes of architectures. I mean, actually, let me put this another way. This theorem that I just gave you applies to transformers and to attention-based networks as it applies to anything else, right? And in particular, and I will touch on that, in a little bit later. In particular, you can take the attention mechanism that attention networks are doing, and you can actually see how it works, in the path kernel. And in fact, one of the advantages of this is that I can actually now have kernel machines with the same attention mechanism that I have in deep networks. But we're probably getting ahead of things a little bit here.
And then Bill was stating, I'm confused. You argue that the weights are superpositions of a feature space in a recursive tree of kernels. In a multiple output neural net, there are actually a superposition of multiple feature spaces, meaning multiple trees. Does this affect the proof?
No.
Affect interpretability?
No. There's only one feature space here.
Okay.
What is the feature space here? It's actually a very simple feature space. Is the space of all the gradients of a particular function, right? For every function, there's a different path kernel, right? Or there's a different space of path, of path kernels, if you want to be precise, right? And the features, what are the features, right? They're not the original features, they're the gradients of the function, okay? So if the original examples were in a 1,000-dimensional feature space, but now, but the neural network has 1,000,000 parameters, I'm actually now in a 1,000,000-dimensional feature space. And in each dimension of that feature space, each feature, if you will, is the gradient of the function with respect to one particular weight. And it's in this space that we're going to be doing the kernel comparisons. I hope this answers the question, but if not, you can ask a follow-up question.
Okay, thank you.
So as I was saying, another interesting set of implications of this is for understanding the empirical behavior of deep networks. It's one of the intriguing things that people who apply both of these methods notice over and over again, right? I mean, this has been happening since the 60s, and in every decade, including the current one, is once you look at it carefully and you use an intelligent form of nearest neighbor or kernel method, etc., you can pretty much get neural networks and nearest neighbor or kernel-based methods to work pretty much exactly the same, right? So empirically, there seems to be a close equivalence between the two, which is strange because superficially they look very different. Of course, now we know that they are not that different after all, right? For example, if you've seen this paper that led to a lot of follow-up work on why deep learning causes, the paper says that to understand deep learning, we need to rethink generalization, right? And this was by Sammy Benchio and a bunch of people at Berkeley and so on. And they basically showed that what these networks were doing at the end of the day is memorizing the data. Even random data points they would memorize. And there are these, all these, application areas, like, for example, captioning is a great example, right? These deep networks that generate captions for images look really smart because they generate, often quite accurate captions for the image. But then what people found was that, most of the time they're just retrieving captions from the training set that happen to be appropriate. And if you just retrieve them using information retrieval techniques like TF-IDF, you do about as well, sometimes a little bit better, sometimes a little bit worse. Which again is very puzzling until you realize that actually, the deep networks are a kind of kernel method. And yet another one is maybe the most important one, another empirical behavior of deep networks that this helps to shed light on is the surprising brittleness of deep networks, right? Which all these adversarial methods take advantage of, which manifests itself in that if you move even a slight distance away from the training example, suddenly your class predictions can easily go haywire, right? You can start predicting that a penguin is a car and very strange things like that. So why this brittleness, right? If you understand that deep networks are a kind of kernel method, this is not surprising because kernel methods are sensitive to the curse of dimensionality, right? And what that means is that in a very high dimensional space, and we are usually in such a high dimensional space, for example, when we have images or large text and so on, is that performance degrades very quickly as you move away from the data points that you have. And that's what we're seeing here. So again, that becomes easy to understand. This may also lead to better ways to combat adversarial methods, in deep learning, but we'll see. But perhaps, of course, the most significant implication of this for deep learning has to do with this notion of representation learning, right? In light of this theorem, I think it's hard to avoid the conclusion that maybe, backprop is not doing as much representation learning as we thought it was, right? It's not like there's no representation learning going on, but the representation learning is going on, a little. I mean, after all, even something as simple as PCA, right, is doing some representation learning, right? Anything that transforms the data into another space is doing some representation learning. And now what we see here is that deep networks are really just, they're one step above that, right? They're certainly better than those methods, but this notion that you're doing representation learning and so you're not relying on predefined features is actually a little bit dubious, because actually now we know that you are relying on predefined features. In fact, the predefined features, as I alluded to earlier, are just the gradients. They're all the feature space is the space of all gradients of this predefined function. And the only thing that learning the gradient is doing is actually selecting which of those features you're using. So in some sense, all that deep learning is doing is selecting features from this particular space, right? And now, of course, the power of that is that you can select different spaces using different architectures and thereby encode, domain knowledge into the problem. But this is a very different proposition from, hey, we're doing representation learning, right? And again, I was always a little skeptical of this notion that gradient descent can do representation learning. Like, how does, what is gradient descent? It's a local optimization technique. How exactly is that discovering new representations, right? Well, I think, in light of this result, we understand what it is and is not learning, right? And I think the bottom line of this for representation learning is that we're not there yet. Representation learning is a very important problem. In fact, it may well be the most important problem in machine learning, but I think we shouldn't be over-optimistic about how far we solved it. I think the representation learning problem is still mostly unsolved, and in fact, as I will touch on later, is one of the most, I think, important other ways. So if gradient descent is really not the solution to representation learning, then we need other better ways to do representation learning, and we need to think about what those might be, and I will touch a little bit on that at the end. Now, those are the implications for deep learning. There's also some very interesting implications for kernel machines, right? One of them, which I already alluded to, is that this actually gives us a great way to incorporate knowledge into kernel machines. You know, through the decades, I've always observed this competition in different research labs between, you know, the neural network folks hacking the architecture to do better, and the kernel machine folks hacking the kernel to do a little bit better. But I think at the end of the day, the neural network folks or deep learning folks these days have an advantage, and maybe the advantage was that it's easier to incorporate knowledge or assumptions or hypotheses about the problem into the architecture of the network than it is to incorporate them into the kernel. And I think this is, you know, a big part of why they, you know, they won out. At least for the time being, they seem to be winning out. But now with this notion of a path kernel, actually we know how to incorporate any knowledge that you know how to incorporate into a deep architecture. You know how to incorporate into a kernel. In particular, the recipe is give me the function that you think, give me the function class that you think the function I'm trying to learn is in, and the feature space that I need to define for the kernel is the space of all gradients of that function. And now, for example, if you want to do a convnet, right, all you have to do is incorporate the corresponding gradients as features, and in particular, do the same averaging that you do when you do, you know, the averaging that, you know, the translation invariance that you have in a convnet, you can actually also have in a kernel machine. Same thing with attention, right? You can actually take the equations of attention, right, and actually turn those into features that are the gradients of that function in whatever transformer architecture you want, and have a transformer kernel machine, and so on. Another one, again, I think a very interesting one, has to do with this notion of the curse of dimensionality. So I was saying earlier that you can understand some of the brittleness of deep networks by realizing that they're kernel machines and therefore also prone to the curse of dimensionality, but they're actually less prone to it than kernel machines or nearest neighbor, and right, empirically, right? And the reason they're less prone, we can actually now understand why, is that they actually have a much cleverer kernel. They're actually using the path kernel. And the thing about the path kernel that's interesting is that it's not doing comparison in Euclidean space as, you know, kernel machines and nearest neighbor traditionally do. It's actually doing the comparisons in gradient space. And doing comparisons in gradient space is actually very interesting from the point of view of combating the curse of dimensionality. Because the thing that really hurts kernel machines, as was studied by Yoshua Bengio and others back when, you know, kernel machines were all the rage, is that if functions vary slowly over instance space, kernel machines will be fine. But if a function varies rapidly, in particular, if a function varies faster than my distance between data points, then I'm hosed, right? Because there's no way I can just interpolate between one point and another and be on the right track, because in the meantime, the function has gone all over the place. If instead of, you know, a Gaussian kernel, let's say, you use a path kernel, now you can actually handle a function with high variation because two data points are similar, not if they're close together in Euclidean space, but if they have similar gradients, right? Which in some ways actually a very powerful thing, right? Right? You know, I could have a function varying, you know, up and down in some small interval and actually totally be able to handle it. Think, for example, of the sine function, right? If I'm trying to learn just the sine function, y is equal to a sine of x, right? Very simple function, right? Trying to learn this using a kernel machine is using with a Gaussian kernel is, you know, is basically impossible until you have points in all the peaks and troughs, or, you know, all around, you know, by Nyquist's theorem, right? You actually have, you need as many data points as you have, peaks and troughs of the sine wave. But if you do this with gradients, right, in gradient space, actually not anymore, right? Because all the peaks have the same gradient, and so what you learn from one peak generalizes to another. All the troughs, you know, all the intermediate points, right? Each intermediate point now has an infinite number of others along the sine wave that is very similar to it, and so now generalization has become massively easier. Okay?
A question from Govind. He was asking, does it mean that kernel functions are as susceptible to neural nets to small changes in input, like adding a few pixels? And I'm interpreting this like adversarial. He continues with this question, how should one interpret GANs in kernel space?
Well, so they are, right? So we haven't solved that problem, right? We've just realized that it's the same, or you know, the same in some sense in both of them. but we haven't. So the experiment that we haven't done, but would be a good one to do, is to see, what. So if we want to use the notion of path kernels to do adversarial learning, right? The question is like, how would you do a kernel based on the path kernel that would be better, right, at combating adversarial examples than what we have now? And I don't have a brilliant answer on how to do that, but I think it's an interesting question worth exploring.
Well, I mean, I can offer. I've been dealing with a lot of real world type of vision recognition projects, and we're trying to constantly imagine the future situations that our applications would be in, and by generating 3D data. So if you were to generate 3D data in an adversarial sense, and you tell it the right class, the right interpretation. So I think there's ways that if you can interpret how you might be attacked, and you can generate that in the training data, you can kind of minimize that effect. That's one offer.
Yeah, I mean, and again, you can probably do that in. I mean, if you think about adversarial examples and GANs and so forth, right? What is really going on there is that instead of just a min problem, they have a min-max problem, right? And in order to minimize well, you need to understand what the maximizer is doing. It really is the essence of what is going on here, right? And now, if you take that math and you plug in the path kernel, right? Maybe you can try to do some of this inside the path kernel, right? Looking at each of the training examples that you have, maybe also figure out where you need examples, right? And actually try to, do a more fine-grained way to combat the adversarial examples than you do with just plain gradient descent. Okay. So last point, and maybe the most important one from the point of view of kernel machines, is scalability, right? The big disadvantage of kernel machines has always been their lack of scalability. At training time, you have to compute the Graham matrix, which is the matrix of similarities between all. You have to apply the kernel to each pair of data points. And then that's all that's needed for the learning, for the optimization. But the problem, which is good, right? Again, once you have the kernels, you don't need the training data anymore because they only enter through the kernels. But the problem is that if you have n training examples, computing the Graham matrix takes n squared time, which means that kernel machines don't scale. And you can, people have, come up with dozens, probably hundreds of ways of trying to, address this problem. But, at the end of the day, kernel machines are not as scalable as deep networks, with something like stochastic gradient, right? And then at test time, right, you need to have memorized all your support vectors, and then you need to compare with all of them, right? And there's efficient structures to do this, but, again, in high dimensions, they basically, become useless. So the cost at both training time and test time is very high. Now, if you look at deep networks or models done by gradient descent as kernel machines, right, something amazing happens, which is because instead of storing all your examples separately as a database, you've actually superimposed them all into a single parameter vector. Number one, you don't have to compute the Graham matrix anymore, because at any point, all you have to do during learning is compare with that vector, which is implicitly comparing with all of the examples that were superimposed into it. And then same thing at test time. So remarkably, right, doing a kernel machine in this way, right, by gradient descent, effectively, means that the cost is now the test cost, the cost of inference at test time, instead of being linear in memory and time, instead of being linear in the number of examples, is now O of 1. It's constant. It doesn't depend on the number of examples. It just depends on the number of parameters, right? That's one aspect. And another aspect is that the big hardware, and you might say unfair hardware advantage that deep networks have in being suitable for GPU implementation is now also true for kernels, right? Computing similarity functions is not as well supported by GPUs as doing linear algebra. But if you do this route, if you use the path kernel and use superpositions, now it does become linear algebra, so you can use that to scale up again, right? And now if you think about it, this idea of scalability via superposition also has very interesting relationships to other fields. Most notably, and has probably already occurred to some of you, if you think about quantum computing, right? The whole exponential gain of quantum computing, the whole reason why we're trying to do it, right, is that you're doing a whole bunch of computations superimposed, right? The superposition is why you can do an exponentially more things in the same amount of time, right? And potentially you can actually do the same thing here, right? Of course, there's a lot to be worked out, but that's, you can imagine also getting such an advantage here. Another simple example is in telecommunications, right? What you get sent through the air is a superposition of transmissions at all sorts of frequencies. They're all superimposed in the one electromagnetic wave that is reaching your antenna. But then you actually know how to extract from that superposition the particular channel or radio station or cell signal that you want, right? And again, this idea of superposition now also applies in a broad swath of machine learning, and there may be a lot that we can do with that. So finally, this theorem, as I said, does not apply only to deep networks. Nothing in it depends on having a deep network architecture. It just depends on having a differentiable model. And when you look at it this way, it actually has broader implications, not just for deep learning or for kernel machines. And let me just touch on a few of them, maybe the most interesting ones. One is that if you look back at the main theorem, another way to look at it is that what's going on here, if you look at the bottom line here, what is actually going on here can also be seen as a type of boosting. So you could also say that a deep learning algorithm is actually a type of boosting. Why is it a type of boosting? Well, the weak learner is the tangent kernel machine, right? It's a weak learner, right? And now I'm going to boost it round by round, and the result of that is the path kernel machine, right? And the weight of each example at each step, right, is its loss derivative, which again is very much in the spirit of boosting, right? Because the examples that have the biggest error should have the biggest weight, so that in the next round I'm able to classify them correctly, or at least to reduce the error in them. And the weight of each model is just the learning rate. So if the learning rate is constant, right, then all the models have the same weight. But in particular, if you set the learning weight by a line search, which is often a good thing to do, and a popular one, then actually what you have is very similar to gradient boosting. Right? And then of course the weight of each model, right, in the boosting is just the size of the step that you took when you did that line search. Okay. And it's easy to see, of course, that each round so what you're doing is like you're adding a series of weighted, tangent kernels, and that each new addition reduces the error until finally converge, or you could also stop before convergence as you're doing boosting. So this also interestingly gives us another way to look at boosting, or another way to look at deep learning as a form of boosting. Another one, and of course the most obvious one, is that if this applies to any model learned by gradient descent, it applies, for example, to graphical models learned by gradient descent. So an interesting implication of this theorem is that a Bayesian network is actually a form of kernel density estimation. Who would have thought, right? And again, the relationship is similar to the relationship between Gaussian kernels and deep networks. It's kernel density estimation done in this smart space that actually incorporates some knowledge via the graph structure of the graphical model. Now, of course, would this still be the case if the graphical models were learned by EM? My guess is that yes, but I have no proof of that. But that's certainly an interesting question. But more generally, right, here's another interesting implication of this. If this theorem also applies to any convex learning problem, regardless of whether gradient descent is used. And the reason for that is if the learning problem is convex, then your optimum is the same, regardless of whether you use gradient descent or some variation of gradient descent or quasi-Newton or what have you. Since they all converge to the same result, and this theorem applies to the result, it also applies to any convex optimization method. Okay? So that's an interesting implication, right? Now, of course, and moving on to some of the future, research directions that this suggests, the question immediately arises: well, what are so if the problem is convex, then this applies, and that's good. But what if the problem is not convex, right? What about learning by other algorithms? What about this, like EM? What about learning by combinatorial optimization? And again, my guess is that in one form or another, this will probably be true, which in essence means that most of machine learning in some sense is learning kernels in one way or another. But of course, I'm just speculating, and this is an interesting direction for future work. Another interesting direction is that if you really like gradient descent and your goal is to improve it as much as possible, which is what a lot of people do these days, looking at gradient descent as computing this path kernel could be a way to improve it, right? You could say, well, gradient descent is only one way to compute one kind of path kernel. Maybe there's ways that will actually work better, right? So a whole bunch of ways of playing with gradient descent arise from this path kernel view that would never occur to you if you're just looking at gradient descent in the traditional way as this local optimization technique and so on. Of course, one of the most important directions that arises from this is what would be better ways to do representation learning, right? I think that unfortunately we have kind of like converged too much on just backprop as the solution to everything. And I understand it kind of works, it scales, and I'm all for it. But at the end of the day, if we want to do representation learning, like really do representation learning, maybe we need something else. So what might that be? I actually think there are interesting ideas from a lot of areas that we can draw on. One of them is predicate invention from symbolic learning, right? Where you don't just learn rules over the existing predicates, you actually discover new predicates, right? And this was
like a genetic programming almost. Yeah, like a kind of like a genetic programming.
Well, that was the next one. So this is in inductive logic programming, right? Typically what you do is you learn logic programs, you learn Horn rules, and then you can try to discover the predicates that appear in those rules. So this is one approach. Another one that I was about to mention is precisely crossover, right? Crossover is a very non-local way to learn things. So maybe crossover can do things like gradient descent or any of these, discrete, greedy optimization techniques, things that they can't do maybe can be done with crossover, maybe with smarter, more intelligent forms of crossover than the ones that have been used in the past. But that's obviously another candidate, genetic algorithms in general, but really the core of genetic algorithms is the use of crossover as the search operator instead of just local search. And another one, which comes from psychology, is structure mapping, right? Richer forms of analogy, right? You can think of nearest neighbor and kernel machines as doing very simplistic types of analogy where you just compare these two vectors, right? And path kernels in a way are still comparing these two vectors, except in a more sophisticated feature space. But structure mapping actually goes beyond that. And there's a lot of evidence from psychology that a lot of our intelligence comes from doing things like structure mapping. Even things as advanced as Niels Bohr coming up with quantum mechanics by doing an analogy between the atom and the solar system, right? That's a classic example of structure mapping. Maybe that's one way to do representation learning. Another one that comes more from neuroscience, also somewhat from psychology, is predictive coding, right? The neocortex, which after all is the seat of our intelligence, does not work by backprop, right? Our visual cortex may look like a convnet to some degree, but it learns in a completely different way, right? And we don't know what it is, right? Maybe backprop is a good model of what the cerebellum does, but not of what the cortex does, right? What is the cortex doing? Well, we don't know, but I think of the various things that have been proposed, the one that seems most intriguing and most convincing is something called predictive coding, right? Is this notion that what your brain does is predict what's going to happen next, and then there's a series of levels where each, if you predict things correctly at the lowest level, you're done. If not, then what you pass to the next higher level is the errors in prediction. So level 1 tries to model the input, level 2 tries to model the errors, the places where level 1 failed, and then level 3 and so on, as many levels as you need, right? And predictive coding is attractive because in some ways it's a very simple principle, but you can get again, in principle, you can get very, very complex, very sophisticated models of reality built up in this way. Now, it's not in a very advanced state yet, either on the neuroscience side or on the AI side, but I think it's another idea that is worth exploring, and who knows what else. But most important of all, and to conclude, to my mind, the single most exciting thing that emerges from all of this, and the one where I personally tend to focus most of my effort is this idea of superposition learning. It's this idea that you can look at almost any model with parameters, with whatever structure you want, and really all it's doing is a superposition and combination of the training examples in some form. This makes a lot of things that seem very complicated suddenly seem a lot simpler, both in the AI case, things like deep networks, but also in terms of psychology and neuroscience, right? If you look at the neuroscience for inspiration, as many people, including me, do, one of the things that strikes you is that it's so hard to understand what's going on because every part of the brain seems to be doing everything. There isn't this simple compartmentalization that you have in an engineered system. But maybe if what you do is, look at what's going on as a superposition of a bunch of different things, each based on having remembered certain specific inputs, maybe many, many few, suddenly, and now you can look at each of these things one at a time, and suddenly it's much more tractable, right? Now, computationally, you might not want to blow things up like that because what's the game, right? But in terms of understanding and in terms of designing things, that's a big help. And then, of course, computationally, right? You get this huge advantage from doing the superposition. And then, of course, the key, or at least one key research question that I find very intriguing is, if I'm going to learn by superposition, and gradient descent is just one way to do superpositions, not necessarily the best one, then the question becomes, what is the best way to do superpositions such that I get the most compaction of the data into the fewest possible parameters or the smallest possible memory, while still remembering enough to be able to do the inferences that I need, right? The thing about superposition that's unintuitive is that you seem to lose information. But actually, in some ways, depending on how you do the superposition, you actually haven't lost the information. The information is still there. You just have to know how to retrieve it. But the other aspect of this, and maybe the most important one for the future, is that it's actually okay to lose some information, provided you preserve the information that you need. And the information that you need depends on the task, depends on the type of prediction or behavior that you're trying to do. And it also depends on, and it may also be good to entirely fail to do supervision from generalization purposes. So how to do this trade-off, I think, is going to be a very interesting question. And I think this could actually be a very rich direction for future research in machine learning. Thank you.
Well, thank you very much. Are there ways that we could use this to, say, debug our neural net? Our neural net is coming up with some forecasts that are generally correct, say in vision object recognition, but we've got some error cases, and we want to understand that. Like with attention networks, can look at salient features, or is there anything out of this idea that we can use, or the quickest way to find what are the training records? Maybe there were some training records that were mislabeled.
Yeah, absolutely. So I think in the near term, this is one of the most obvious applications of this result, is precisely for debugging deep networks. Debugging deep networks is incredibly important and incredibly hard. And the way this gives us to debug deep networks is precisely to say, so this network is getting something wrong, right? It's making an incorrect prediction on some example or set of examples, right? How do I understand what the network is doing? Well, the answer that comes out of this is, give me the training examples, maybe even just the single training state example that is closest to the example that you're getting wrong in gradient space, right? And you can also measure, how much that example is accounting for the result, right? What percentage of the weight, or even say, I want to look at as many examples as account for 90% of the weight, or as account for the decision that was made and it was just, X% of the weight, right? And then it must be, if those examples are mostly determining the output, it must be that the error is coming from them, right? And now you can fix the error by fixing those examples, by removing them, by modifying them, changing some features, by adding in you can actually go, if that's an option, and get examples that will compensate for those, right?
But what's the mechanism? Like, let's say if I had something really simple like k-nearest neighbors, then I have my training set of k-nearest neighbors, and I could take my new record that's not being predicted correctly, and I could look at if k is 5, at the 5 neighbors that are closest to it, and I could explicitly look them up. It would be expensive to compute, but I could look them up explicitly. and then I could check those 5 nearest neighbors and see if some of those were mislabeled. What would be the equivalent for this for a deep net?
I mean, so exactly what this does is that it makes debugging a deep network the same as debugging k-nearest neighbors.
But
Everything
then
that you do,
how would I find out like my 5 closest records to my misforecasted?
because they are just, so in traditional k-nearest neighbor, you would find your 5 closest records in Euclidean space, right?
Yeah,
That's irrelevant here, right? We're not in Euclidean
of
space
course.
anymore. What you do is you find your 5 closest records in gradient space, right? You find the 5 closest records according to the path kernel, right? Remember, you have the path kernel for that network, right? And you can compute that path kernel for any pair of examples that you want. In particular, you can compute it for your test example that you're getting wrong and for each of the training examples.
So
And
then
then
the
you
path
find,
kernel is just the dot product of each input times a given hidden layer, and
no, simpler than that. It's not the product of the it's not the dot product of the inputs. It's the dot product of the gradients of the weights, right? Right. Remember, what's happening here is that like you are now in a new feature space, right? You're just going to do nearest neighbor in a different feature space, right?
in the gradient feature space.
Right? How in particular is the feature space being computed here, right? Is that each feature in that space, each dimension, is the gradient of the function that you define by the architecture with respect to one weight, right? So if you have 1,000,000 weights, you actually have 1,000,000 features in this space, right? So you know how to compute that using the path kernel, right? You can just write the, I was going to say you can write the program, but you don't even have to because you already wrote the program, right? You know, when you did the learning, you just have to gather the weight vectors that you obtain, and then you get like your similarity in gradient space.
So if I have 100,000 training records and I have 1,000,000 weights and I have a new record, then I have to take those 100,000 records and calculate the for each of those records the 1,000,000 weights, and that's the basic space I'm trying to see what I'm closest to for this new record that's being misforecast.
So not the 1,000,000 weights, but the 1,000,000 weight gradients with respect to each of the derivatives with respect to those weights. But yes, so
Right.
I think what you're pointing to is that this is horribly expensive, right? A lot of examples and a lot of features, right? But notice several things, right? It's not more expensive than training the network, right? And usually, for debugging purposes, you actually have a lot more time than you have at performance time, right? Number one. But then number two, right? There's a whole bunch of stuff that you can do in terms of, making this more efficient. Like, and we know this from, all these different areas. Like, you can try to pre-select what the most likely relevant examples are. You can pre-select the most relevant features, et cetera, right? So there's a whole bunch of things that you can do to make this more efficient. But, it might still be expensive, but I think when you're trying to debug a deep network, and if you have a nice number of GPUs, you're probably willing to pay that expense.
Yeah, understood. Other questions from the audience? Oh, Bill is stating this seems to assume that the weights converge. I mean, I think that would be the case if we have a network going into production, but what's your comment, Pedro?
No, actually, this does not assume that the weights converge, which is nice because sometimes often these days we use networks without converged weights. Notice that there was nothing at all in my entire treatment, in my definition of path kernel, or in the theorem that requires the weights to have converged. This is true. So this theorem is true after one step of gradient descent, after two, after any number. It's completely irrespective of whether it converges or not. The one thing that no longer applies is this equivalence that I mentioned at the end between, gradient descent or doing something else, right? So for this to apply to any method that's solving a convex optimization problem, of course, what that relies on is that the solution is defined by the optimum, and then that is not reached if you don't converge. But as far as ordinarily trained neural networks that use whatever early stopping or some fixed number, this applies without any change.
Okay, very good. Well, I think we've gone through the questions. So thank you very much, Pedro. This has been a very good talk. Let me see. Christian is asking, the path kernel is a sum of dot products in gradient space. Does one need the training history to compute the nearest neighbors?
Well, yes, you do. right? That's why this is expensive, right? And that's why I do not recommend using this as a learning algorithm in its own right, right? Because what it means, so to compute, so this thought experiment that I mentioned of like, I'm going to run my test example through the training process and compute the gradients and, and the corresponding tangent kernels, right? Doing that requires having remembered the weight vector at each step, okay? So if you have n steps, right, this is n times more expensive to store than the final network, which is crazy, right? In particular, if the network is big. If the network is small, then never mind. So I would never recommend using this as an algorithm in its own right. But as I said, the advantage of this is both what it does for us in terms of analysis and in terms of interpreting things, and possibly in terms of the starting point for future research directions. Yeah. I think, there's, again, there's a lot to be done there. I think there are probably ways to take advantage of this idea that would mostly avoid that cost or bring it down to something reasonable. I'm pretty sure that to compute a pretty good approximation of the path gradient or the path kernel, you don't really need to have remembered every network along the way, right? You can probably just remember a crucial, because if you know how gradient descent works, right? There are places where it's making fast progress, but most places it's making very little progress, right? So there's probably here's an optimization that I could do. Find me a small number of intermediate networks that to within delta gives me the same result for my purposes of applying the full path kernel, right? So there's a whole bunch of things like that you can do.
Question for me: would you or anybody in your research group be considering releasing any kind of code that would help debug, say, TensorFlow networks, something that's more specific and tangible on GitHub?
We don't have that yet, but hopefully we will within the foreseeable future.
Okay, very good. Yeah, anything to help find those bad or weak examples for debugging the network would be very good.
Yeah.
Okay. Well, thank you very much for your time. It's been a very good talk. So I'd like to close it out.
Greg?
Yes?
Yeah, there's just one post announcement I think we should make if we're at the right point for that.
Go ahead.
So actually, Bill, Lou, it might be a good time for you to come in and make an announcement about your event that you are having, I think, in 2 days, right?
Yes, thanks, Bill. We from AI Camp, we are hosting Applied AI Summit 2021. Actually, this is coming Wednesday. We have speakers from Google, Pedro Domingos, and also speakers from Facebook and Goldman Sachs, a few other high-profile speakers talking about deep dive into AI and machine learning, deep learning technologies, and particularly for the enterprise AI. It's free and online, exactly like this one, and interactive. So feel free to sign up if you are interested. I can post the link to the chat.
Okay.
Thank you.
That was all I wanted to say, Greg. Thank you.
Okay. Well, thank you very much, Pedro. We really appreciate your time for the talk, and there was definitely a lot of questions and interest in it.
Thank you.
Yes, thank you. Very interesting stuff. Yep.
Okay.